In this video, we are going to be studying gravitation inside the Earth and due to an extended body. It does not correspond to a particular section in your textbook, but it's interesting and necessary to some extent to study gravity in different scenarios. We know what happens when an object gets further from the Earth's center. The gravitational force gets less, and so does the acceleration due to gravity. But what happens if a particle is inside the Earth and gets closer and closer to the center? So two things happen. Number one, the gravitational force would tend to increase because the centers of the two objects would be getting closer together. The other thing that could happen is the gravitational force would tend to decrease because there is less effective mass acting on the particle. So you can see in this picture, as this person gets closer to the center, there's less of the Earth to act on them. If we assume a uniform Earth, then this number two scenario outweighs, pun intended, the first scenario. What eventually happens is the gravitational force would be zero at Earth's center because there's the same amount of mass causing a force in all directions, so the forces cancel out and add up to zero. Now, it's different if we consider what happens in real life. In real life, the Earth does not have a uniform mass density. In reality, a gravitational force on the particle increases as the particle begins to descend, and then the force reaches a maximum at a certain depth and then decreases as the particle descends further. So here's somewhere in outer space, and acceleration is on the y-axis. As we get closer and closer to Earth's surface, acceleration due to gravity increases. That makes sense. Now, what we just learned on the previous slide is we would expect it to do this green line. That's if we assume a uniform density. However, because the density of the Earth varies throughout its layers, as we go from Earth's crust down into the outer core of the Earth, the acceleration and the force due to gravity actually increase because it's so dense. So there's a lot of mass acting on the particle. Now, once it reaches this point, it'll decrease as the particle gets closer to the center. Now, for this first example, we are going to be assuming a uniform Earth. What is the gravitational force on a particle of mass m at a distance x from the center of a spherically symmetric planet of uniform density ρ, total mass m, and radius r when x is less than r? So first, let's visualize this. So this circle is our planet. This little circle represents the effective mass acting on the particle. And here is our particle, and it's a distance x, which is less than r from the Earth's center. So our normal formula for force of gravity is this, and I just called it m within because we don't want the whole mass of the planet. We just want the mass that's actually acting on this guy, and we don't have to consider the mass out here because it's uniform on all sides, so it'll just cancel out. For example, this mass up here, this part of the mass of the planet up here, will cancel out with this up here. We just care about this mass inside here. So we know that the planet has a density m over v, and it's uniform, so whatever chunk of the sphere you take, it'll have the same density. This is the whole sphere. Oh, and this should actually be to the third. And this should be to the third as well. Sorry about that. So this is mass divided by volume. Still mass divided by volume equals the density. Now, the density of this smaller sphere will be the same as the density as the whole sphere. So the mass within the small sphere will be equal to the density times the volume. The density is what we got from right here, 3m over 4 pi r to the third. And then the volume inside this sphere is just 4 over 3 pi x to the third. So in this case, the radius inside the sphere is x. So m within is this whole thing, so we can just go ahead and plug that in right there. After we simplify it a little bit, so we have F equals G mx to the third over r to the third times m, and then all of that over x squared. We can simplify it quite a bit, so these x's will cancel out, so you'll end up with G big M little mx over r to the third. Now sometimes what you'll see textbooks or the AP exam do is they'll take out this chunk and call that K. So they'll say F equals Kx, where K is equal to GMM over r to the third. And they just like doing that because this is in the form of Hooke's law, where it's equal to some constant times x. So the force is proportional to the distance. Now we're going to do it for a non-uniform planet. So we have the same setup, except there's a non-uniform density of rho. So again, it's just the force is equal to the gravitational constant times the masses times each other over the distance between the masses squared. And we know that the mass within this sphere is equal to whatever density is here times the within volume. And we just leave density as rho. We don't actually know what the density is. We just know that it's non-uniform. We don't know what this function is, but we know that we can just use the letter rho. So we plug m within back into our equation for force, and we cancel things where we can, and we end up with 4/3 g rho pi mx. Again, what you'll see textbooks and or the AP exam do is they'll take out this chunk and call it K so that it can be in the form of Hooke's law. The last type of problem we'll be doing is gravitation due to an extended body. So Newton came up with something called the shell theorem, and it says that a uniform spherical shell attracts a particle that is outside the shell as if all of the shell's mass were concentrated at its center. So these two spheres attract each other as if all the mass is here and here. So it makes our lives easier if it's a sphere. However, if the object is not spherically symmetric, the gravitational force must be calculated using calculus. That's what we're going to be doing on the next couple of slides. So we have a uniform slender bar of mass m and has a length dl. And we want to determine the gravitational force it exerts on the point of particle mass m shown. Sorry, bit of a typo there. So we know that it has a linear mass density because it says that it's uniform. And the linear mass density is m divided by L. Now what I've already done here is I have this little chunk of the bar with a width dx, and that'll correspond to it having a mass of dm. So the linear mass density is also equal to dm over dx. If we solve that for dm, we get that dm equals lambda dx. Now, here's the part where we have to use a little bit more calculus. So we know that the derivative form of the gravitational force is equal to this point particle mass. So obviously the gravitational constant, this point particle mass, and since this is an extended body, it's dm and then over r squared being the distance between each of these little masses and the point particle. Now, if we integrate both sides, we can get the force. Oh, and we know that dm will be what I just found here, and that r will be equal to whatever this distance is plus each of these little mass distances. So that's z plus x squared. So we integrate both sides, and it goes, we want to integrate it from 0 to L. And I'm going to take out anything that is a constant. So g is a constant, m is a constant, and lambda is a constant. And if you integrate it, you get -1 over z plus x. And then if you take in the boundary conditions, you get this. You can simplify it. I'm going to do that on the next slide. So I plugged in L here, that's where this comes from, and I plugged in 0 here, that's where this comes from, and it'll end up being -1 over z plus L plus 1 over z. So that ends up being 1 over z minus 1 over z plus L. And we get this. So what I did from here to here is I put them both over the least common denominator. Simplify it. And you get this. And then for lambda, you can go back and plug in that m over L. That's what I did down here. So these L's will cancel out, and you'll end up with g lowercase m big M over z times z plus L. Sorry about that. So that is that problem. You had to use calculus to solve it.